Hi, my name is Zach, and today I'm going to discuss secondary stability and periodicity for unordered configuration spaces of manifolds. These are patterns in the homology of configuration spaces. I'll start out by giving you a little bit of background and telling you about a classical phenomenon called homological stability. This is a pattern for homology of configuration spaces of non-compact manifolds. After that, I'm going to tell you about some more recently discovered patterns. The first pattern, secondary stability, is another pattern involving configuration spaces of non-compact manifolds. The other two patterns, periodic stability and periodic secondary stability, are patterns involving configuration spaces of compact manifolds. Throughout this talk, I'm always going to assume that M is a connected manifold. In addition, on this slide, I will assume that M is non-compact. I'll denote the unordered configuration space of k points on M by conf k of M. As a set, it is the set of all unordered k tuples of points on M. Since M is non-compact, there is a map called the stabilization map, which I'll denote by S, from the configuration space of k points on M to the configuration space of k plus 1 points on M. The idea behind what this map does is captured by the picture on the slide, and it's as follows. Since M is non-compact, we can assume that M is the interior of a compact manifold with boundary. What the stabilization map does is, given a collection of k points on M, there is a way of bringing in a point near the boundary infinity to obtain a configuration of k plus 1 points on M. In the 1970s, McDuff and Siegel showed that the stabilization map induces an isomorphism on integral homology for all k greater than 2i. This result is an example of a phenomenon called homological stability, and the range where homological stability holds is called the stable range. Homological stability is a pattern that many important groups and spaces, families of groups and spaces in math have. For example, general linear groups, mapping class groups, automorphism groups of free groups, and Hurwitz spaces all have homological stability. In addition, homological stability has had many important useful applications. For example, it was important in Quillen's calculation of the algebraic K-theory of finite fields. Now, one question one could have about these homology groups is, are there any other patterns that they have outside of the range where homological stability holds? In my research, I showed that if one considers the mapping cone coming from this stabilization map, then there is another stabilization map, which I'll denote by S2, called the secondary stabilization map, which induces an isomorphism on integral homology from these relative homology groups for all k greater than 3i over 2. The idea behind what this secondary stabilization map does is captured by the picture here. The idea is, given some homology class in the relative homology, there's a way of bringing in 2 points from the boundary instead of 1 point and having them do a half twist around each other. This isomorphism that I showed is an example of a phenomenon called secondary stability. Secondary stability was a pattern first described by Soren Glacius with Alexander Coopers and Oscar Rana Williams in their work on mapping class groups. It is qualitatively different from homological stability because now, whereas before you didn't have any relative homology to really consider, here you do. In addition, unlike before where the homological degree was fixed, now the homological degree is shifting by some term. In my opinion, it is a worthwhile question if many of the spaces which have homological stability also have secondary stability. So up till now, everything I've been talking about has been assuming that M is a non-compact manifold. And so you might wonder, what happens if M is compact? Are there similar sorts of results and patterns? In order to answer this question, there are two issues that need to be addressed. The first issue is that if M is a compact manifold, there isn't any obvious stabilization map from the configuration space of k points on M to the configuration space of k plus 1 points on M. As a result, we have no way of taking mapping cones or considering if there's any sort of secondary stability. The other problem, and this appears to be more serious, is that we know from explicit calculations that the homology of configuration spaces in this case doesn't stabilize in general. For example, Fidel and Van Buskirk showed that the first integral homology of the configuration space of k points on the 2-sphere is isomorphic to z mod 2k minus 2 for all k greater than or equal to 2. Now, this might look like to be a serious problem at first, but if you sort of stop and think about it for a minute, there's still a pattern that can be observed. By the universal coefficient theorem, one can show that in this particular case, that the homology with FP coefficients for the configuration space of k points on the 2-sphere will be isomorphic to FP when k is congruent to 1 mod p and p is an odd prime, and it is 0 otherwise. And so the point is that even though the homology is still not going to stabilize when we consider homology with FP coefficients, there's still a new kind of pattern here, namely that the homology is going to be periodically isomorphic with period p. And it turns out that this calculation embodies what happens in general for the homology of configuration spaces of compact manifolds. And that's basically due to the following result by Federico Quintero with Martin Palmer, Rohit Nagpal, and Alexander Coopers with Jeremy Miller, who showed that if M is a compact and connected manifold, then the homology of the configuration space of k points on M with FP coefficients is isomorphic to the homology of the configuration space of k plus p points on M with FP coefficients for all k sufficiently large. Now, I would consider this to be an example of sort of an abstract periodic homological stability statement, because all it says is that there is, as FP vector spaces, these two homology groups are isomorphic. And all these people were able to do is produce some sort of zigzag between these two groups. But they don't produce a map on spaces, let alone even on the level of homology, which induces this isomorphism. As a result, it's a little bit unsatisfying because it gives us no way of knowing if this isomorphism is natural, for example, and also it gives us no way of investigating if there's any sort of secondary stability phenomenon. Now, it turns out that all these issues can be addressed by working at the chain level instead of working at spaces. So what I did in my research is I constructed basically new models for these configuration spaces, and I constructed a new stabilization map which induces the isomorphism in the previous slide. In addition, I constructed a new secondary stabilization map for configuration spaces of compact manifolds, and I showed that when p is an odd prime, this new stabilization map induces an isomorphism of relative homology groups with FP coefficients for all k sufficiently large in terms of some constant depending on p, the homological degree, and the dimension of the manifold. And this isomorphism is an example of a new kind of phenomenon, and I would call it periodic secondary stability, because unlike before where I was considering configuration space of k plus 1 points on M relative to the configuration space of k points on M, now we're considering configurations of k plus p points. And so there's a period p phenomenon here happening, and in my opinion, it makes it qualitatively different from secondary stability for non-compact manifolds. That's all I wanted to say about my work. Thank you for listening to my talk.